wave, and we say it's the ability of the wave to always move in one plane polarized. So now our next topic is, like I gave you the topics today. So we know that the first was to talk about the properties of wave. I've done that. Now I'm going to the second topic, which is the mathematical representation of a wave. You know, as waves travel progressively, they have a mathematical representation. Remember this, you have, if you did your trigonometry well, you must have seen that if you plot the graph of sine theta, now you have a graph like this. If you put sine 30 here, this is, let's say I have a table like that. Now we'll have x and y. I have 0, I have 30, I have 60, then 90, and so on, 120, 150, and so on. So now if you punch sine 0, that gives you 0. You have sine 30, this is 0.5. You have sine 60 is 0.87, so we call it 0.9. Sine 90 is 1. This sine 60 is still 0.9, and so on. If you punch this on your calculator, if you press it, you have, let's say if I plot this graph like this, you have 90, now 120, and so on. So we have you have 0 for that, and you have, let's say, 0.5, and you have 1 there. So this is 0.5, and this is 1. This is 0.30 is 0.5, and 60 is 0.9 somewhere there. And 90 is 1, so have somewhere there. And 120 is 0. That, 120, and so 150, and so on. So you see that when you plot this, you're going to have a shape. Maybe we'll pass through, if you can do it properly, you see that it pass through and form a graph like this. So if you plot a graph like this, it's going to look like a wave, like just what I've told you. Remember when I represented the wave, I told you waves are sinusoidal. That's why we call them sinusoidal wave, because they take the shape of a sine graph. So this sinusoidal wave, for as much as a wave is parabola, that parabola has an equation. In mathematics, you know the parabola having an equation of y equals to ax squared plus bx plus c. You know that already. That is for all parabolas. So now this kind of, this wave here, the a here is going to be negative because it is an n-shaped graph. So now, if equations in math, also parabolas in math have equation, then as the wave is progressing, the wave also must have an equation. So now, that's just a background of what I'm trying to do here. So now let's look at the mathematical representation of a wave. If a wave is represented mathematically, since we know that it is a progressive, the wave progresses in this form. From the background there, you know what we did before. So we have the crest of the wave, remember the trough of the wave, and we say that the time it takes to complete a circle is the period, you know all of that. Now, and we know that the amplitude of the wave was that. Now, in this diagram, we can now use mathematical ideas to sort out an equation for this wave. So now, if I look at the semicircle here, I have a semicircle somewhere there, that is this. Then I have another semicircle somewhere there, that's it. Now I must have got a full circle. So a full circle, I'm now playing this, then I fix the full circle, so I start from there. So you now know that I've taken the semicircle, another semicircle to give me a full circle. So if I want to represent the wave mathematically, so our topic is supposed to be mathematical representation of a wave. So I can move this and now give you the real topic, that's mathematical representation of a wave. Of wave. Yeah, clean this so that we want to use that. For the benefit of the viewers, let me represent it properly. Representation of wave. So we can represent the wave mathematically. So we have that equation somewhere there. Now remember I just brought it down for you a little bit. So we see here, let's say a wave that was vibrating on a visual position, that was the wave. We look at a particle. The particle is somewhere there. Now let's say that particle is the visual position that is displayed at an angle theta, and it must have gone through an x displacement and also a y displacement. So this amplitude, this is the radius of that circle, so that must have given you the amplitude. Let's say the wave was here, so this amplitude, this is amplitude 2, so have the amplitude there. So that's the wave displacement. That's the maximal displacement of the wave from its rest position, remember that? So now that visual position of the wave is represented by that. And let's say we take that triangle out. If I take the triangle out, I will have theta over there and A, and I have Y there. So if I do the maths properly, you will see that it's going to be Y equals to something. Here, sine theta is supposed to be equals to opposite over hypotenuse. So now Y must be equals to A sine theta. Now that's one basic wave equation. Now if the wave is supposed to move, if the particle is too traversing in circular motion, we move with a velocity. So that's velocity, let's call it omega. For as much as the particle is moving in that circle, this circle came from that wave motion, remember that? So that I bring it down, you now have the two, so have omega, we know that is velocity, so we call it angular velocity, that is angular displacement over that. So it is the angular displacement because it started from here, the particle, let's say, started from the origin here, and now moved to that point, it has been displaced at an angle theta, and time elapsed, there was time for that movement. So now we have theta as equals to omega t. Omega is the angular velocity, you know that already. So I put the two into that, I have A sine omega t. Now if I put this into context, you have that equation coming out. That is the equation, I'm just modifying that equation. So what if the wave decides, the particle goes and conducts a circle? If the particle conducts a circle, remember what will happen? It will now go through 360, and the time it takes to conduct that circle is a period, and 360 in radian measurement is 2 pi, you know that already. So now I can fix that, so I can say the omega complete circle is 2 pi all over t. And before, we described the relationship between speed and frequency, so we can rewrite this properly, and we now have 2 pi f. Because if I fix this one in there, it will go. I substitute the reciprocal of the frequency inside the period here, I will get that equation over there. So what if you now have a wave that is moving in another particle that's having a visual position, like there is a particle somewhere here, let's say Q. And remember, this is the wavelength. Now that wavelength, or this one, is also one wavelength. So now if I have a particle that is of a phase difference of x, that is the path difference, and that path difference has a relationship between its phase difference. The phase difference is given by this, so we can have this phase difference. It's an equation given by phase difference all over 2 pi is equals to the path difference all over lambda. So if I fix that there, I'll have phase difference as phi in that case, so I have 2 pi somewhere there. Then I have the path difference, that's the path difference x over lambda there. So the phase difference becomes 2 pi x all over lambda. So now I've got that path difference. So if you look at this, there's a link between them. The phase difference is directly proportional to the, but all of these are constants. So we have, let's say, phi as equals to kx, where k is the constant of proportionality. So that our k will be something like 2 pi all over lambda. So now we have, and that k is called the wave number. This is called wave number. Wave number, that constant is called the wave number. So if I can now have this equation put inside here, if the wave is now moving, let's say a visual position of that wave somewhere there, another particle somewhere there, it has, if that's phase difference, that's a phase difference. So our total angle now becomes, now instead of that, I have the total angle, which is now theta plus phi. So now I have y is equals to sine, instead of theta, now I have y is equals to sine into theta plus phi. Now if I come back to my equation, I will have sine, a here, a sine, now I have omega t plus. Now this phi was the kx somewhere there, so I have kx. But it's possible that the wave can be moving in different directions. So I have plus or minus kx, because the wave is moving in different directions. So now it's x for wave, if minus here, the wave is moving from left to right, that is minus. If wave is moving from right to left, that is plus. So that's why I place plus or minus, because wave can move in either direction. So now if I come back and introduce all my variables here, if I put that a, I'll have sine Now omega is 2 pi f. That is from here. I've just substituted the omega. So somewhere here, I was able to fix it there. So now we have the omega here. That is what I've substituted for you, and the t. Then I also substitute for the k. The k is 2 pi lambda. So I have 2 pi lambda and bring my x somewhere there. So now I know from wave that we have frequency lambda. So I can now make f the subject of the formula. So f is v over lambda. So if I fix it back inside that equation, I will have a sine into 2 pi. Instead of that f, I'll put v lambda. Then I put t, then plus or minus 2 pi lambda x. Now if I factorize, I'll factorize here properly. So I have a. Now if you can look at this 2, you have a common factor there. Sine, common factor is 2 pi lambda. This is 2 pi lambda. If I take it out from that box there, I'll have vt, then plus or minus, then I take it out there, I'll have that. So this equation represents the equation of a wave. This is the mathematical representation of the wave. It tells you how the displacement of the wave is moved with respect to the time. And this y is telling you the displacement. A is the amplitude, and you have the speed and time and all of that stuff. So now if you look at this, we look at the question on the board, we can now use this. So remember, this x, this plus or minus, the wave can be moving from left to right, right to left. So here we have that equation from there. Now we want to move with the question on the board. So the question on the board is telling you that find the, see that the following is representing the wave profile. So now use that equation to figure out the amplitude, figure out the other variables there. So the first is that. Now remember, from that equation, we were able to look at the path difference, the relationship between them. So remember that the equation is giving us y equals to a sine omega t plus or minus kx. Yep, so now with that, we can compare that equation. So look at the question on the board. It says the equation represents, so if I compare it, I'll have that from that question, 0.04 sine into omega is 1360. Now 360 pi t, and we have plus or minus in this case 18 pi x divided by 36. Now, so if I compare that equation, so I can write this properly. If you like, you write a sine. Now this can be written as 2 pi f, that's omega and t. Then minus, I'll have 2 pi lambda x, if you like, because this is k, remember that stuff. So now if I compare the two, I can find out that this variable, this all of this represent that. If I compare that, and this represent that, if I compare that, and now look at this one also represent that. If we're comparing coefficients, because the left hand side are all equal, so the right hand side, the coefficients are also equal. So you can look at the two. Now, if you, in this question, you are not asked to find the amplitude. So let's say the first question was amplitude. So the amplitude is supposed to be now 0.04. Amplitude was measured in meters, remember that. Now we have the next there is going to be to find the frequency. So if I look at the equation there, this frequency is found inside this. So I have frequency, which is omega, which is 2 pi f, as compared to here, it is 360 pi. So if I get the pi and the pi vanish, so I have 2 and I have 360. So if I divide here by 2, divide here by 2, this guy goes. So this is going to give us 180 hertz. So that's the frequency of the wave in that case. So if I compare, then I'll go back to the period. It says find the period. So remember, the period is the reciprocal of the frequency. So the period is the reciprocal of the frequency. So now we can look at the period as 1 all over 180. This is 0.125. Let me just use my calculator. This is 1 divided by 1 divide 180. It's 0.005 something, 0.005, that's 6 seconds, if you like. You can write that 6 times 10 raised to the power minus 3 seconds, if you like. So now this is the period. So you've got a period over there. So now we look at the next one there. It says find the speed of the wave. The speed of the wave, it's given by that equation. So we have frequency lambda. So we needed lambda. Lambda can be, you can get lambda from that. So k is 2 pi lambda. And you substitute that, you compare, you have 18 pi all over 36. So pi will vanish with pi. So I have 18 lambda is equals to, this is 72. So I just cross multiply from there. So you see the 18 and these two will go. So I have 18 and this 18. So lambda will give you this 72, 7, 2 divide 18. So you have, this is 4 meters. So we have 4 meters. So now we have the lambda as 4. So we can find the speed. The speed is frequency lambda. Remember that? So we have F, which is 180. And now we have 4. So we have the lambda is 4. The frequency, remember here, this was 180. So now I have 180 divide 180. Now multiply in this case, multiply 4. So we have 720. So 720 is meters per second. So we have the V. So what I've done so far is to give you the speed, now the frequency, the period, and the speed. Now I want to move with the last question there. It says, what is the phase difference? The phase difference, remember that phase difference was this, which was 2 pi there. What was the phase difference at some point, x. So now this x can be the displacement at a point. This is here as the position of the wave particle at that point, as the position of the wave particle at some later point, and with respect to the first position. So now the first position there is 1/8. So we have 2 pi lambda, if you like, into. Then the second position, if you check the question, the first position was at 0. That's 0.32 and 0.1. So 0.32. So if you look at the first equation there, is 0.12. So I say the first position is 0.18 and second position is 0.32. So meters. So I substitute there. I have 0.32 minus 0.18. And this gives you a total of that answer. It gives you rads per second. So this is the phase difference. Now that gives you the end of that question. So I thank you for your audience.